this video is going to look at the different properties and applications of logarithms kind of as a whole. So the first thing we're going to look at is we are going to look at how to use properties of logs, so the product rule, the quotient rule, the power rule, in order to expand. So the key word for this one is expand. Expand means we're going to take something small and we're going to make it much bigger. So something small is the fact that we have all of this stuff here inside these parentheses, and to expand it out says that we want to make this larger. So we want to break these down by the properties we have. So if you look, I have 4 times x squared times the square root of y. So the first thing I need to look at is I need to look at your product rule. So the product rule says that you are going to expand everything through the use of addition. So we're going to have the log base 2 of 4 plus the log base 2 of x squared plus the log base 2 of the square root of y. So that's considered to be like the big expansion. However, we still have more rules and more properties that we can use. For starters, we have this 2 right here, and this is actually going to be your power rule. And when you're working with your properties, it's always a really good idea to work your properties kind of one at a time. So if we look at this first piece, we know I have the log base 2 of 4. This can actually be evaluated. When we do that, you end up with 2. My power rule, remember, says your power comes down to the front. So this becomes 2 log base 2 of x plus the log base 2. And for my square root of y, I'm going to rewrite it using powers. So this is going to be y to the 1/2. And the reason for that is because, one more time, I have right here my power rule. So this is going to end up being 2 plus 2 log base 2 of x plus 1/2 log base 2 of y. Now, since we don't know what x and we don't know what y are, and there's no other rules for us to use, we would be considered done. Let's look at another one here. So again, we have to look at what is the rule we have. We're trying to expand, and in this one, the first rule that we have here has to do with this little center bar. So this would be your quotient rule. And the way I like to think of these is I like to think of them kind of like, well, I guess in the words of my mom, peeling back an onion. What I mean by that is you have to look at the outermost rule, or the biggest most rule you have. Start with that one and work your way down. I have 3 times a to the 5th on the top, and I have the square root of b cubed on the bottom. But the biggest rule I have here is my quotient rule. That's where I need to start. And your quotient rule says you have to subtract. So this becomes the log base 3 of 3a to the 5th, and we are going to subtract that from the log base 3 of the square root of b cubed. Now, with that, we have to continue to apply or break things down even further. So if we look at this first piece here, right here, we have your product rule. So it's a good idea, like I said again, to kind of break things down piece by piece. So we're going to work just with this first part and then we'll come over to the second. So to break this product rule down, now we're going to have the log base 3 of 3 plus the log base 3 of a to the 5th, and then we still have that minus log base 3. And the only thing I'm going to do here is I'm going to change that square root into its power form. So this is going to become b to the 3 over 2. So what we need to remember here is that this numerator part is considered to be your power. Your denominator here is your root. Okay, so we had a square root, so we put it over 2. Now I have to keep going, and if we look at this one, right here I have this 5. So this is going to be that power rule. And this piece out in front, we are going to do and evaluate. So here we have log base 3 of 3. Well, that's going to give you 1. Plus, my power rule says that 5 comes down to the front, so this is 5 log base 3 of a. And then we have minus the log base 3 of b to the 3/2. So again, with that, I have this piece here, which is another power rule. So to finalize my problem, we're going to end up with 1 plus 5 log base 3 of a minus 3/2 log base 3 of b. And since there's nothing else for me to do to try and simplify it down any further, that's how I know I am done. I've got no other rules or properties to use. Alright, let's look at one that's in a natural value state. So the biggest thing that we have to remember when dealing here with the natural value is that this is going to be the same as saying log base e. Okay, so we can use that idea to rewrite. Now the other piece that we have is if we look inside here, again we can start out with that product rule. So we're going to do both of those concepts at once. So here we're going to have the log base e, and we're going to use that product rule. So we're going to have the first part of 2 plus, now we're going to do the log base e of e to the 3, and we're going to add that to the log base e of x to the 5th. So now with that, I have log base e of 2, so this is not going to evaluate well, so this can become back to natural log. It's another way to shortcut. Here, if we look right here, we have a power rule. And so the power rule again comes down in front, so this becomes plus 3 log base e of e. And then if we look at that back one, notice again right here my 5 is going to be another power rule. Again saying it comes down in front, so this becomes plus 5 log base e of x. Continuing to simplify everything down, we have right here log base e of e. So what we're going to do with that is we are going to evaluate, because the log base e of e is going to be 1. Now the other thing that we have here is if we look, there is nothing to simplify to, so we have to use the natural log rule. And the only reason we do that is to make it look a little bit cleaner when we are putting together our results. And so here we would end up having the natural log of 2 plus 3 plus 5 natural log of x. And that would be the end result. Alright, so that is expanding. Now what if we want to go the opposite way? So notice here my big fancy word to remember is the word condense. Condense says that we're going to take something really big and we are going to use the properties and rules to shrink it down itty bitty. Okay, we want to make it as small and as tight as we possibly can, using as many rules as we can fit. So the easiest thing to do is to look at these step by step. Okay, so the first thing I always like to do is I always like to verify that my bases, so this little number down here, is the same on all of my logs. And notice in this one all of them are a 4, so they are all the same. So you want to work piece by piece. Okay, so the first thing that we have to do is notice that I have this 5 here on the outside, which is going to be your power rule. So working backwards, that means this first part is going to be the log base 4 of x to the 5th. Then we're going to add this onto the next one, which is the log base 4 of y. And we're going to subtract the last, log base 4 of z. Now you're going to work left to right. Okay? So what we're going to do here is we're first going to take the addition piece, and this is going to be our product rule. So the product rule says if you're using addition, then you can condense it back down using a single logarithm, so log base 4, and this is going to end up being x to the 5th y. And then we're going to minus the log base 4 of z. The last thing we have is this subtraction piece right here, which is your quotient rule. And so that quotient rule says that we are now again going to condense down, so we've got the log base 4. The stuff on the left hand side is going to be your numerator, so this is going to be x to the 5th y. And then the stuff on the right hand side is your denominator, so this is going to be over z. And that is our condensed version of this exponential problem. Alright, let's take a look at another one here. So when we look at this first one, again, remember you have to work kind of from the inside out as much as you can. And so the first thing you want to do is right here, because this is your power rule. And so before we do anything, you need to use the power rule. So log base 5 of x, and we're going to minus the log base 5 of y to the 4th. Now the only other thing we have left to do here is our sign, and this sign here is going to be your quotient rule. That quotient rule again is division, and so this is going to end up being the log base 5. We're going to have that left hand side is your numerator, so this is going to be x over. The right hand side is your denominator, y to the 4th power. Alright, let's try another one. Again, we need to start with any kind of power rules you may have. So I have a power rule here, so that's what this says. This is your power rule. So we're going to go ahead and start there. So this becomes the log base 3 of a to the 4th, and we are going to subtract that from 1/2 log base 3 of b. Again, we have another form. This right here is your power rule. So we need to use that again. This becomes the log base 3 of a to the 4th minus the log base 3 of b to the 1/2. And then we have to look at your sign because there's nothing else, no other power rules to use. And again, once again, we have your quotient rule. And that quotient rule says, once more, the left-hand side is the numerator, the right-hand side your denominator. So this is going to become the log base 3 of a to the 4th all over b to the 1/2. But then we need to remember this denominator right here means root, whereas this numerator here means power. And so the last thing that we always need to consider doing is we need to consider rewriting it in terms of our root, not just the rational power. So here the other way that you would write this would be the log base 3 of a to the 4th over the square root of b. Now for most, either one of these examples would be perfectly acceptable. If you're ever confused or not sure, the easiest thing to do is to ask your instructor or your teacher which method that they are using, but both of these methods mean the same thing. It just depends on how they want to see your results. Okay? Do they want to see the radical form or do they want to see the rational form? Alright, let's kind of do one more here. Notice this one has lots of natural logs. And so let's go ahead and take a look at how that's going to work. So the first thing we have to do is the same thing as always. We have to work from the outside in, but we have these parentheses here. And what that says is that we have to do what's inside your parentheses first. So this here, because of this plus sign, is going to be your product rule. And so your product rule says that we have the natural log of x minus 2 natural log of x plus 2 times x minus 2. If you look at this 2 here, this is going to be your power rule. And so here, this is going to end up being the natural log of x minus the natural log of x plus 2 times x minus 2, and then we're going to square it. This right here stands for your quotient rule. So this is going to end up giving us the natural log of x over x plus 2 times x minus 2, and we're going to square it, but we have to go one step further. This power rule here has to be applied to both of your parentheses. And so here what we're going to get is the natural log of x over x plus 2 squared, x minus 2 squared. Alright, now another concept that we talk about a lot when dealing with exponential functions and logarithmic functions is, or specifically log functions, is being able to evaluate your expression when you have a weird base. So notice this base here is a decimal. So in order to do that, you have to use what's called change of base. And the change of base is a rule that goes as simple as this. If you have log base A of B, well, that's going to be the same as having the log of B over the log of A. Okay. Now that same idea can be applied to your natural log. So again, if we have we can use the natural log of B over the natural log of A, just depending on the problem we're working. Okay. So for this first one, to use change of base, we would simply evaluate the log of 1200 divided by the log of 2.4. And you would use your scientific calculator for this. You would use your log button. And one of the rules that you always have to remember is if you don't have a base written, it's called common log. It means the base is actually a base of 10. And so what we would be doing, I can pull out my calculator. Now again, remember, this is the TI-36X Pro, so your calculator may be slightly different than mine, which means your log buttons may be located in a different area than mine. But the root concept is the same no matter what the calculator is. Okay, so here what we're doing is on my calculator, you can see right here I have an ln and a log button, and so I want to go ahead and use that. So when I click it the first time, notice it shows ln in my window. I want the log, so I just simply click it again and then input my value. So this is going to be 1200. I'm going to close it, and I need to divide that by the second one. So I'm going to go back and I'm going to hit that button twice again so the log appears, and I want 2.4. I hit enter, and there you have it. That is your result. Now in this problem we wanted the nearest thousands. Thousands means 3 places. So we have 8.0986. The 6 tells us to round 8 or round up. So here we would end up with 8.099 as being your result. Pretty simple. So let's try it one more time. In this one, I'm going to have the log of 1/14 divided by the log of 5. Again, I would use my calculator, so let's go ahead and pull that back out. Let me clear the window. And we're going to do the exact same thing that we just did. So we're going to hit our log button, so the log shows up, so notice it says log. And then here we want to do 1/14, so 1 divided by 14 and close it. Then we're going to divide, and we want to do log of 5. So this is going to be log, so again notice my window says log, and this is 5, and hit enter, and there we go. So here this is going to be negative 1.640. Now let's talk about that real quick. I want 3 places, so I have 6397. So notice the 7 is going to round that 9 up. 9 rounds up to 10, so this actually becomes 40. Okay. Alright, now what happens if you're asked to evaluate or simplify without a calculator? So let's look at that again real quick. In order to do that, what you need to always remember is your rule for going back and forth. So here what we're going to end up having is we actually have 5 to the x is equal to 1 over 125. The easiest thing to do is to change this so that we can actually end up heading towards the same bases. So we're going to take this and we're going to say that we have 5 to the x is equal to 125 to the negative first power. So what we're doing is we are using the negative rule, but we're reversing that negative rule. So the next thing that we're going to do here is we need to change 125 down into 5. So this is going to be 5 to the x is equal to 5 to the negative 1 times 3. So now what that really means is that we have 5 to the x is equal to 5 to the negative 3. The rule says if the bases are the same, your powers are equal, so therefore we know that x is equal to negative 3, and this would be your answer. Alright, let's try that one more time. Here I have the natural log of e to the third. So the first thing that I would do is I would use my power rule. So if you look on both of these, notice I have this third power and I have this half power. So both of these are going to use your power rule. So let's go ahead and apply that. They come down in front, so this ends up being 3 natural log of e minus 1/2 natural log of e. With both of these, my natural log of e's, here what we have to do is evaluate. Because the natural log and the e are opposite of each other, which means they undo each other. So this is going to actually give us 3 minus 1/2, which is going to give you 2.5 or 2.5 as a result. Now the last one here says I have the log of 75 minus the log base 5 of 3. So we need to use one of your rules. This rule right here is your quotient rule. So the quotient rule again says I'm going to write the log once. The left side is my numerator. The right side is my denominator. So this here is actually going to give me the log base 5 of 25. So when I'm looking at that, I have 5 to the x is equal to 25. And if we just look at this, common sense says what? 5 squared gives you 25. So we know that x is going to be 2. However, if you want to write it by changing your bases to be the same, this becomes 5 to the x equals 5 squared, which gives us x equals 2, and thus your answer. Now really the last thing that we end up looking at, or you doing a lot with logarithms, is we have what I like to call just the weird, crazy applications. Now the cool thing about these applications I'm about to show you is these are actual examples of real-world applications. In fact, this first one we're going to look at is dealing with earthquake intensity, and this is actually an idea that is currently used to measure actual and real earthquake intensities across the world. This is what our seismographs do. This is kind of how the analysis is. So it's a real kind of good connection. So this one is talking about the 1923 Tokyo and Yokohama, Japan earthquake. Now they measured that earthquake to be 8.3 on that Richter scale, and the question wants you to work backwards. It wants to know the intensity. So here's a little thing about earthquakes. When you have the seismographs going off, what the seismograph is actually doing is it's measuring the intensity that is going on. We then use an equation to calculate that Richter scale that then gets reported. Okay, so that 8.3 number is actually calculated. The way that they calculate it is they use an equation that says R is equal to the log of your intensity over your initial intensity. Okay, so R stands for Richter scale number. I stands for the intensity of the earthquake, and the I naught stands for your zero level. Okay, so again, the R here is going to be your Richter scale number. The I right here is going to be the earthquake intensity. And the I naught is your what's called a zero level intensity. Okay, so that's how the formula works, and this is a formula that does get used to measure. So how does this actually work for this problem? Well, obviously the piece that we don't know in this particular problem is the earthquake intensity, but what we do know is the Richter scale. We know the Richter scale value, and we know the zero level value. So we have to plug in the information we know. So this is going to be 8.3 is equal to the log of your intensity over your zero level, which was 1. And so we have to be able to work backwards. And so the way that we do that is we need to remember when there is no base written, the base there is actually 10. So just like with everything else writing backwards, what we really have here is we have that I is equal to 10 to the 8.3, and you would go ahead and do that in your calculator, and we're going to come out with I being 199,526,231.5. Now, for anybody who is confused about how to plug that in your calculator, let's go ahead and take a quick look at that and clear this out here. So we are going to do 10 to the power of 8.3, so we're going to put in our 10. Now, in my particular calculator, I have this X to the box button. Okay. However, some calculators have a button that has X to the Y. Okay, so you could look for a button like this one. They also might have it looking as Y to the X. Okay, so it could be like that. Or you might just simply see a caret or a hat-like button. So any of those can show up and they all mean the same thing, but for mine I've got this X to the box, so notice that's going to offset my value. And I just simply plug in the 8.3 and hit enter, and notice that's exactly what I have here. 199,526,231.5, and so that is the intensity of that earthquake. Alright, another real-world example for using logs is finding the pH of water given a certain concentration. And so we have a formula that we use here to find pH. So your pH is calculated by the negative log of your concentration. Okay? And so essentially what you're given in this problem is you're given your concentration value and you have to find the pH. So here you plug it in, so your pH is going to be the negative log, and we're going to take the log of 2.3 times 10 to the negative fifth, and it's moles per liter. So in this case, my pH here would come up to be 4.64. Now we use this pH in order to determine the acidity or the base or basic of a solution, meaning is it too acidic, and that can be very dangerous, is it too basic, which can be very dangerous, or does it fall within normal neutral standards. pHs are calculated in many different ways. We use them to calculate or look and evaluate water. We can evaluate the pH of a blood system to make sure that a person is functioning the way they're supposed to. We use pH evaluations with swimming pools. So there's many different applications for that, but the root base formula for how you would calculate it is the same. So this is the formula we use here, and it's pretty simple plug and chug method. Alright, the last one I wanted to look at is sound. So here this question wants you to find the intensity of sound given that your initial sound level is 10 to the negative 12 watts per square meter, which corresponds roughly to the faintest sound that can be heard by an actual person. So that is the decibel level that we can hear. Now, with that, we again have a formula. So in order to find your decibels, we have that D is equal to 10 log of the intensity over the initial. Okay, and that is the formula we use to calculate the decibels of whatever sound it was you heard. Okay, so if you think about a plane flying overhead, or a car backfiring, or a truck, or a bike slamming on their brakes, a dog barking, somebody shouting, the TV going off, all of those different things have different sound intensities, and we all hear them at different intensity levels. So here we're going to find out what the actual decibel is for a faint whisper and for a diesel truck that's 25 feet away. Okay, so let's start with the faint whisper. We've told you here that the initial intensity for a normal person is going to be 10 to the negative 12, and here I'm telling you the intensity of that faint whisper is 10 to the negative 10. So to find the decibel says we simply plug information in that we have. So this is 10 times the log of 10 to the negative 10 over 10 to the negative 12. So you'll use your scientific calculator to go ahead and plug this in, and once you do, you should come out with 20. Okay, or 20 decibels. Now let's go ahead and look at that diesel truck. It's the exact same concept. So here we're going to have D is equal to 10 times the log of, the diesel truck is going to be 10 to the negative third, and again our initial is still 10 to the negative 12th. So when we plug all that in, we end up with 90. So clearly what you can see, the smaller your decibel number, the softer or quieter the sound. The larger your decibel number, the louder and larger the sound may be. So that's what you need to know kind of about properties of logs and some different application that can be used in more of a real world setting, kind of breaking away from that normal everyday crazy math problem. So if you have any questions, please let me know. If you have any examples or application problems that you need help solving, let me know those too. I'd be more than happy to work them out. Otherwise, I hope you had a lot of fun, and I'll see you next time.